Lecture 8.3, the diffraction parameter and its meaning. How much a wave bends / diffracts around an obstacle / slit depends on its size of the obstacle / aperture and its wavelength. A wave bends most around an obstacle when the size of the obstacle is comparable to the wavelength. In other words, A, the size of the obstacle, has to be somewhat comparable to the wavelength. In some sense of the word, the wave sees the obstacle better if this is the case. So to see an obstacle with waves, we must, one, you have to change the shape of the wavefront. You have to change the wavefront. Otherwise, you can't see if there was anything. And another thing here, that if a detector is placed it must measure a difference in wave pattern / intensity. So what we want to do here is that we want to use an applet sort of give us a sense of what it is, and then we'll go into the details. So the first thing I want to do here is that I want to assume a wave detector is placed behind some obstacle. And now what we're doing here is that we now have incoming waves that now diffract around the obstacle. And there are three possible cases. One here, A is much, much bigger than the wavelength. So this is a gigantic, a very large barrier. So this would be a large barrier. The other one is that the wavelength is so much bigger than the obstacle. This tells us that we have a very small barrier. And then finally, we then have the wavelength comparable to the size of the object. So what this tells us here is that we really see the obstacle in this situation. So what I'm going to do here is that I'm going to go share my screen and go look at the applet. And then we'll adjust the values so you can see what I mean. So the first case that I want to look at is I want to look at a large barrier. So let's go look at that. So now what we want to do here is we're going to use this applet to actually look at the situation where we have a very large barrier. So let's go change the parameters here. So I need to make the wavelength as small as possible, and I need to make the obstacle as big as possible. And what you're seeing here is that there is a very, very strong geometric shadow right here. Now, the other thing that we want to look at is that we want to make the wavelength as big as possible and the obstacle as small as possible. And what you can see here is that note that the waves don't really change that much. And now we want to make the wave comparable to the obstacle size. So in this case, we're setting them equal to each other. And what you're seeing here is that if you look off to the left or to the right, note that there is definitely a change in wave pattern. Okay, so now I want to go back to my applet, my OneNote, and then start talking about this. So the first thing that we did here, so the first one is I have this applet, right, this one right here. So what I'm going to do here is that I'm going to put in, here's my obstacle, I'm going to put in my detector right here. Right, so this is my detector. And when I look at what this wave detector is doing here, well, because it's in a geometry, so in this situation, again, we're looking at the values that we just talked about it. Here, we chose the wave to be much smaller than that. What you're finding here is that there is a strong shadow region, geometric shadow region behind the obstacle. So then the question is, what is it going to see here? Well, it's not going to see anything. So this means here is that there is the waves do not diffract well behind the barrier or the obstacle. Then we looked at the other situation where we had this guy now. And what we're seeing here is that one more time, what I can do here is that I could copy my wave detector and place it right here. So if I place my wave detector here, this detector won't really detect anything. So in this situation, you know what? I'm going to run out of space. So I'm going to have to move this guy a little bit closer to this guy right here. Uh-oh. Let me try again. So now if I paste in my wave detector again, what I'm seeing here is that in this situation, the wavelength is much, much bigger than the obstacle. So there is very little change in the wave pattern. So immediately that tells us here is that the waves, the detector detects no difference and is invisible. That's like throwing a cork into an ocean. The ocean waves are so big and the cork is so small, you can't disrupt the waves. And then finally, we have ones where we're setting them comparable to each other. So in this case, what we're doing here, let me bring this guy down a little bit more. We're seeing here that the wavelength is comparable to A. And what we see here is that one clearly sees a change in the wave pattern. And therefore, by studying this change, one can deduce what the obstacle is. So that's a very fundamental of how the diffraction parameter really plays a role in this. So now, to give you a sense of where I'm going to go with this, I want to do an example. I want to look at, as an example, I want to look at sound and light diffraction. So here we go. So the first one I'm going to look at is that I'm going to look at sound diffraction because you are very familiar with it. You may not use these words, but you're definitely an expert. So assume that my back is pointing towards the classroom audience. Why is it that you can hear my voice even though I am facing away from you? It's the same thing what happens in a doorway. If I'm lecturing in my classroom and you are off to the side of a doorway, why is it that you can hear me even though you're not in front of the door? So picture-wise, I imagine something like this. I imagine that I have a whiteboard. So I imagine that this is my whiteboard. And this is the back. So let's say that this is the whiteboard. And what we know about the whiteboard, it's smooth, so we should have specular reflections. Now what I'm going to do here is that I'm going to draw my head here, maybe a little bit further back. So here's my head. And as I'm talking, what's going to happen here is that the waves reflect off of the wall. So I imagine that the waves are reflecting off and they're now moving around my head. And so what we'll say here is that these guys are the reflected waves. This one right here, this is my head, and the audience is right here. Too many students. And so what you're seeing here is that this is the audience, and what the audience is that they are the wave detectors. So now what we got to do here is that what actually happens, the fact that you're hearing my voice really means that the waves have to do what? They are coming and they are diffracting around my head as the diffraction starts to occur. So now, let's write this here a little bit here. So now my voice reflects and interacts with my obstacle head. And we're going to say that my obstacle head, let's say it's about 20 centimeters. So then let's say that my sultry voice has a frequency of 120 hertz. And if I remember correctly, that's my fundamental. And the air in the room is room temperature. Because of its room temperature, that implies here is that the speed of sound at standard temperature and pressure is 340 meters per second. The wavelength of my voice is then going to be, so the wavelength of Carlos is then going to be the speed of sound divided by the frequency. So that has to be 340 divided by 120 hertz. And therefore, I get roughly around 3 meters. So this is the wavelength of my voice. Now let's calculate the diffraction parameter. Calculating the diffraction parameter gives that A over lambda will be about 0.20 meters, and this is going to be 3 meters. So this is 0.07. In other words, this tells us that the wavelength is much, much bigger than A. So what this tells me here is that the fraction is very small, and the sound waves bend easily around my head. So what I'm going to do here is I'm going to go back to that applet, and we've already taken the image of that applet. And so what that's telling me here is that the obstacle is really small. So if I look at this thing here, what I'm seeing here, I'm going to look at this, and what this is really telling me here is that, once again, excuse me, if I have my wave detector here, what we're seeing here, again, let's just say that this guy right here, here's the wave detector. What we're going to see here is that we see that right in here, that there is very little change in the wave pattern. And you hear my voice clearly. You hear my voice clearly. There's no diffraction. That means no minimas / maximas will occur in the room. Now what we can do here is that we can repeat this for light. So now let's repeat this same thought experiment but now we will shine. Doesn't really matter what color of light we shine. Let's say that we just used orange. How about if we shine orange light? And in this case, orange light is about 600 nanometers onto the whiteboard. So then if I come back here, I'm going to copy this since we've already had this. And then I'll just modify it. So in this case, what we're seeing here is that we already know all these details. So I'll just get rid of them. And what we're really talking about is that now we have orange light that's reflecting, right? We have orange light that's reflecting. So the question is, what is this orange light doing as it now interacts with the head? So what we could say here is that now we say here that the orange light reflects and diffracts around my head. So the question is that how much diffraction occurs? So the diffraction parameter shows that A over lambda, in this case, it will be 0.20 meters, and this is 600 times 10 to the negative 9 meters. Well, you could see here is that this number is enormous, which tells us that now A is much, much bigger than the wavelength. So this tells us here that my obstacle head is very large and light will not diffract much. Therefore, it causes a strong shadow region. So when I look at this thing, if I come with my picture here, we're going to see here is that right here, I'm going to have a strong shadow. The wavelengths are too small. So as a consequence, you're seeing this orange light, but it's not getting behind my head. It's the same reason right? So let me write this here. So this is my shadow region. It's the same reason that when you shine a light outside of a room, the light does not bend around the corner, right? When you shine a light, it goes straight. But the reason why it goes straight here is because it doesn't diffract well. Whereas sound, on the other hand, does diffract well, and therefore it gets behind the obstacle. So again, using the applet again, right? Using the image, from the applet, this is the situation that we get. You could see here is that now, if I have my detector right here, it's in a strong shadow, right? Right in here, we see that this is a strong shadow, and therefore does not diffract well.